In 1929, Henry Busk published an influential method for constructing cross-sections through folded strata, in which the layers were defined by concentric arcs. Busk's key point was that precision in section construction is all important. Previously, we looked at how this precision is applied to draw a cross-section that uses surface geology and a well to construct a continuous folded layer. Since then, I've coloured in the layer that we constructed so we can see it more clearly over the construction lines. But now I'd like to continue to draw the cross-section, pushing our interpretation deeper into the subsurface. And this will promote a discussion about the difference between the concept of precision and accuracy. But let's go back to the cross-section. Let's draw a new horizon that's another 200 metres below the one we've drawn already. And remember that at the scale of this, the scale bar is 5 centimetres long, so 200 metres is going to be 1 centimetre on the cross-section. So I'm just going to draw in some 200 metre marks in here, just there and there. And the first one we can draw is very easy because these two construction lines are parallel, therefore this line segment is a straight line, and we can simply draw that in. And everything seems to be working fine, where that layer is 1 centimetre, 200 metres in reality, thick, and we're going to propagate this on through the diagram. Right, so it's time to get the compasses out, so I'm going to put my point on here to continue propagating my arc. Let's stick it onto there, and we're going to draw that arc now in to continue our horizon in to there. Now, when faced with a little conundrum that's coming up, and it'll be obvious what that is in a second if it's not already, well, let's just move to another part of the section, and we'll come into this area in the core of our antiform from this side over here. So I'm just going to get the ruler out again and measure down 1 centimetre along that construction line. So that tells us where the new horizon we're constructing lies beneath the one we've constructed already. So we can go to our construction point here, pop it on the limits of the compass to there, and draw it in as an arc to that point there. Oh dear, these are not matching. And you can see in this position in here that, well, the layer's going to thin, something's going to happen in here, but it's not working very well. Well, let's just quickly push on and complete the rest of the diagram for now. Draw it around to there. I'll just have to extend this construction line down. While I'm at it, I'll extend that one because that's where we're heading in our next arc, like that, and those ones are fine. So let's continue. So this time our arc point is in here. We put the compass on the end of the bed as far as we've got and push that one around. That's looking pretty good. So we can continue that one there to here. Oops, that's not very good, is it? Let's do that again. That's better. That's better. I'll just erase that one. There we go. There's just a little tiny piece in here that we can do, which I won't really try and do because it's going to be very fiddly. We'll join it up freehand just to make it work. I'm just going to use and construct this arc. So 1 centimetre, 1 centimetre there. So this, from this point in here, we can just pop that on and sweep it around. So that's working all right. And if we had a really detailed set of compasses in here, we could construct that arc, but it's at the limit of this particular instrument. So I'll just join it up freehand, roughly like that. So that's working all right. And of course, finally, we could put this bit of arc in right round to here, just to complete our profile to the other side. Yeah. Like that. And again, we get to this point in here, and we've more or less eliminated this little arc segment in this position. So there's our constructed profile. And we've got this problem that we identified very early on, that in the core of this antiform, we've got this mismatch problem. And that's a fundamental problem of the Busk construction. It works very well for this one horizon in here, but as we move away from the initially constructed profile, other layers fail to join up, and we have these construction anomalies. So what's the cause of this mismatch? Well, you might argue that it's because we're using this rather hopeless compass bought from a supermarket, and if we'd gone back to the 1920s, we'd have a better set of drawing equipment. So we could think that maybe this is the result of imprecise plotting. But actually, of course, it isn't. It's the method itself is generating the mismatch. In other words, it's not creating an accurate interpretation where the bed that we've tried to draw should make a continuous layer throughout the fold structure. So the method is precise, but it's not accurate for those parts of the section we're interested in at the moment. Let's just look back at the original single layer interpretation. This single layer could be constructed properly because the centres of curvature lie outside the layer, and there's plenty of room for the arcs. But as we've added the new horizon, this arrangement has been lost. And as a consequence, the method has broken down. It may be very precise, but it's proving to be inaccurate in that it's not generating a viable geological interpretation. There's another issue with the Busk construction technique, that as you move away from the data and the original horizon that you've constructed into other parts of the section, either above or below ground, then the folds lose amplitude. And clearly that's an artifact of the construction technique. The real world doesn't have the highest amplitude folds where we happen to see them at outcrop. Well, this apparent anomaly with the Busk construction arises because of the central assumption that folds are developing as concentric arcs. In a pack of layers, it's actually geometrically impossible to fold them all as concentric layers where they maintain thickness. There has to be other things going on. And if we look at this natural example, which actually comes from the south coast of Sicily, you can see that the layers that are gypsum, well, those layers are maintaining thickness, but the lower strata are having to pull away from the thicker one. There's actually mud in this section that's been washed out by the sea, so that we have a thickened hinge area and thin limbs between the two layer types of the gypsum. So the method works for single isolated layers which are relatively strong or competent, encased in incompetent material, and that incompetent material flows to make up the difference between the folding competent horizons. Clearly the method's very good at constructing the competent horizons. It's not at all appropriate for constructing the form of the incompetent material. Actually, this limitation on the Busk construction was recognised actually back in the 1920s and is reported in the review of Busk's book that appeared in Nature. So people were fully aware, as indeed Busk was, that the method was not universally applicable. Busk's book goes into great length, not only on the method, but also talks about the assumptions and the requirements for strata to have continuous layering in them, and indeed he spends some time justifying these assumptions. Precise techniques of section construction have become routine since the development of the Busk construction, and they're far more elaborate than this simple model for concentric arcs. But all rely on the basic requirement that the understanding of the deformation is appropriate to the construction technique that we are using. Busk's ambition for precision in cross-section construction is laudable, and indeed these days in modern structural geology the use of software to create precise cross-sections is commonplace. But the thought that precision alone will increase the quality of subsurface interpretations is wrong. Precision without understanding the assumptions behind the methods or the suitability of those methods to the structures at hand generates an overconfidence in the solutions that are being proposed for subsurface structure, and can lead to expensive surprises when engineering decisions are based upon them.